Hello, friends, and welcome to episode 5 of this monthly structural basics series where we talk about structural engineering, my journey creating content online, and my life being a structural engineer. This is the February update. It's gonna be the last video where I'm 27. I'm turning 28 on Monday. In these monthly episodes, I'll share one story of the month, one structure tip of the month, and an update on structural basics. All right, let's get into it. Story of the month. This time I want to show you guys how my days as a structural engineer looks like. When do I get up? When do I get to the office? When do I leave the office? How do I manage to work so much on my job and on structural basics while I also hit the gym 4 times a week and prepare for a marathon? I got a lot of these questions from you guys, and that's why I want to answer them in this video by showing you my routines and the structure of a typical weekday from morning to evening. All right, let's jump into it. I usually get up at 5 a.m. I'm a morning person. I'm most productive in the morning. That's why I like to get up very early. Once the alarm hits, I get out of bed, I put on my training clothes, go to the bathroom and brush my teeth. Next, I meditate for 10 minutes and do a breathing exercise for 4 minutes, which is followed by some stretching exercises to prevent injuries. I'm training for a marathon right now, which means I run almost every morning. Mondays and Fridays are for easy runs, Tuesdays for tempo runs, Thursdays for intervals, and then a long run on the weekend, which is usually more than 20 kilometers. I'm usually starting my run at around 5:40 a.m. Okay guys, it's 5:40 now. It's freezing cold, it's -4 degrees. And we're gonna do a 10k tempo run. Good speed. It's not an easy workout, but let's get the work done. Alright, I'm done with the run now. This was a real tough one. 10k. Pace was 4 minutes, 30 seconds. Now I'm gonna shower, get dressed and ready for work. And I'm getting back between 6:30 and 7 a.m. depending on how many kilometers I run. Once I'm back from my run, I take a shower, get dressed, and then leave the house between 7:15 and 7:30 a.m. But this varies always. I take the metro to go to work. This takes around 30 minutes from door to door. So I get to the office around 8 a.m. Then at the office, I first get a coffee and water, and then I start my laptop. I'm working in the buildings department for a structural engineering company with over 200 employees in 8 locations. The Munich office, basically where I work, is quite new, and we're around 20 people there. But most of my colleagues work in other departments like the bridge or infrastructure management department. Currently, I have quite a lot of projects. I think it's around 5 to 6. So every day and week looks quite different. And yeah, probably every week I work on, let's say, 3 to 4 different projects. So whenever I get to work, I'm kind of deciding which project I have to prioritize, what tasks need to be done. But yeah, once I started my computer and once I also had my first sip of coffee, I get started on one of these projects. It's like 2 school projects in the early design phases. So we're coming up with different variants. Also, I'm pre-dimensioning the elements, so the architect can do like cost estimates. And yeah, these school projects are partly new buildings and partly refurbishments, which I quite like because it's very challenging, because you have to work with what's there and find solutions, and you cannot just make the elements bigger. Then I have 2 certification projects. In Germany, you always need to get your structural designs checked by a second engineering office with a certified engineer. And these certified engineers, they have decades of experience. They're like the best engineers in Germany. And I think across Germany, I think I read we have 500 to 600 of these certified engineers. And basically with this certification, we make sure that there wasn't a mistake in the structural designs. And if there was a mistake, we're kind of like, making notes that the size needs to be increased or whatever. Oh yeah, and I forgot to tell, I'm basically helping our certified engineers to check their projects, because usually it's like a normal engineer checking those projects, and then a certified engineer who has a meeting with you, and you go through all of the critical things of the project, and then they kind of consult you and sign in the end. Yeah, so one of these projects is it's actually 4 precast concrete buildings, and the other one is a refurbishment of an old manufacturing plant with steel structures, machine foundations, crane tracks. So a lot of like very advanced stuff. Then I'm designing a manufacturing plant myself with precast concrete and timber elements. And another project includes a vibration analysis of a 30-meter tall steel staircase. And it's no beams, it's just plates. And it's a really old tower. It's like, I think, 1,000 years old. And they want to put in like a new staircase so visitors can actually go up the tower. It's pretty cool. The great thing is that all of these projects are kind of like a great mix of different structures. I get a lot of new structures. I get a lot of refurbishments. I can work with all 4 materials: masonry, timber, concrete, and steel. And my work mainly includes doing a lot of structural calculations, which I teach and show you guys here every week on my YouTube channel and in my free newsletter. If you want to sign up to that newsletter, then links are in the description below. Then I also do a lot of sketches of the structural systems and elements and dimensions of those structural elements. I usually use Bluebeam for that, and then also writing structural design reports. I usually have lunch with my colleagues anywhere between 12 p.m. and 1 p.m. It takes anything between 30 minutes and 1 hour to eat and talk. And then back to work. I really try to work as efficiently as possible. Try to get into flow state. I usually listen to music. My colleagues are also very passionate about their job, and they're also super focused on kind of delivering the best possible product to our clients, which is usually drawings and reports, or like finding the most cost efficient and sustainable structure. And that's really nice to be surrounded by people who share the same interests and are very passionate. So on a normal day, I finish work between 5:30 p.m. and 6:30 p.m. I leave the office and go to the gym. I try to get through my workout as quickly as possible, because a day only has 24 hours, and I'm also already spending so much time working out and at work. So a workout usually takes me between 50 to 60 minutes. Then I get home, cook and eat dinner, and in case it's not already 9 p.m., which is usually the case, but if not, I start my laptop and work on a new newsletter or a new YouTube video. And a routine I developed is that at 9 p.m. sharp, I go to bed. Earlier, whenever I kind of like wasn't tired and it was 9 p.m. and I continued working until 10 p.m. or whatever, I couldn't fall asleep, which meant that I was either more tired the next day because I didn't sleep as much, or I slept in, or like I didn't get up at 5 a.m. and slept until 6, and it kind of like mixed up my whole routine again. I really go to bed at 9 p.m. every day. Then I usually watch YouTube videos or a series until 10 p.m. And then from 10 p.m. I try to fall asleep. And usually it doesn't take me that long to fall asleep. And once I fall asleep, I'm getting up the next morning. In most cases, very sharp, to have an amazing next day and an amazing day at work being a structural engineer, delivering the highest quality structural designs. Structure tip of the month: vertical load transfer. When we structural engineers design a building, our job is basically to transfer the loads from the roof and floors through the structural elements and down to the foundation and then to the soil. By doing that, making also sure that all the structural elements don't fail. Here is a 3-step process of how to transfer vertical loads from the roof to the foundations. Step 1 is defining the static systems of all of our structural elements, like beams, columns, slabs, walls, footings. Then step 2 is applying the vertical loads like snow, wind, dead and live load to the structural elements they act on. And then step 3 is the load transfer from the top to the bottom using the static systems. As simple as it sounds, transferring vertical loads through a building is not that easy. In our structural engineering degrees, we're not taught how to design structural systems like buildings, warehouses, parking garages. We only get taught tiny little systems of this big system, like a simply supported beam or a continuous beam. And then by having the static system of this element, we then try to design simply supported reinforced concrete beams. Always in those examinations or these university classes, the static systems and loads are already given, but we don't really learn how we get to those loads and to those static systems. So the question is actually, how do we actually pick the right static system? Should I use a simply supported beam or a continuous beam? Should the connection be a hinge or a moment stiff connection? Where does the line load of 5 kN per meter on the beam actually come from? And what happens with the reaction forces? To design a building, a canopy or a warehouse, we need to understand how vertical loads travel through a structure from the roof to the foundation, from one structural element to the next. Vertical load transfer is a very complex topic and you need years of experience to master it. There's still some design situations where I kind of like question, okay, which static systems I have to use now, and I actually ask my colleagues who have more experience. Every material also works a bit differently. The type of connection determines what forces are transferred to the next element. There are endless examples. A hinge connection between a beam and column will only transfer vertical loads to the column, but a moment stiff connection will suddenly also transfer moments. Instead of using beam and column as the static system, we should actually use a frame to calculate the internal forces. Okay, now a lot of theory. Now let's run through an example. Okay, for our example, we use a basic structure to understand vertical load transfer from slabs to beams and then to columns and then to a point foundation. Okay, step 1, static systems of the structural elements. Without knowing the static systems of the structural elements, we can't transfer the loads through the elements correctly. In this easy example, our slab is a simply supported beam. The beam is a simply supported beam as well. And then the column is also a column with a pin support at the bottom and a roller support at the top. The easiest static systems you can pick are simply supported beams and columns. In terms of vertical load transfer, because you don't have any bending moments in the supports. For example, precast hollow core slabs are examples of simply supported floor beams or slabs. But for example, in situ slabs supported by columns and beams cannot be modeled as simply supported beams because they are continuous. So at the points of support, they have moments. And in that case, we cannot do a simple vertical load transfer, but we have to use advanced calculation methods like the finite element method. But this example here is a perfect start to understand vertical load transfer. Step 2, applying the vertical loads. Let's say the design load of the slab is 5 kN per square meter. We apply that to our slab. And now in step 3, we transfer the load, the 5 kN per square meter, from the top to the bottom using our static systems. We apply the load to the static system and calculate the reaction forces. These reaction forces are then applied to the next structural element. So in the next step, we calculate the reaction forces of the simply supported beam. So we apply the 12.5 kN per meter as a line load to a simply supported beam, and the reaction force is calculated as 43.75 kN. And this reaction force we then apply to the static system of the column, the 43.75 kN, which you can see here. And then finally we can also apply this point load to the pad footings
which you can see in this picture. Note that we didn't include the self-weight of the structural members. In this example now, if it's a reinforced concrete structure, you should definitely include the self-weight because it might even be the biggest load. With those loads on the static systems of the structural elements, you can go ahead and calculate the internal forces, and then based on those internal forces, you can design the structural elements for bending, for shear, and then the footings you can also design for its geotechnical properties and design, of course, reinforcement on concrete. I have written a very detailed blog post where I actually added 4 more of those examples. So if you are still unsure about vertical load transfer, go check that out. I'll leave a link in the video description below. Okay, update on structural basics. As of today, February 22nd, we are 11,599 structural engineers subscribed to the Structural Basics newsletter. We had about 40,000 people visit our homepage structuralbasics.com in the last 30 days. And on YouTube, we have grown by 231 people in the last 28 days. We're now 3,084 people subscribed there, which is amazing because we just hit another milestone, the 3,000 subscribers. Thank you for everyone who is subscribed there. On the newsletter, we published 4 articles. The topics were content creators within structural engineering that I follow, how to use beam analysis software to calculate internal forces and deflections, design of reinforced concrete beams, and how to design reinforced concrete beams with software. I'll leave links in the description below to all of those articles if you're interested to read them. Well, that was it for February. I hope you get value. I hope you return. I'll see you in the next one in March. Peace.